Welcome back to another explainer. Today, we're diving into something that sounds straight out of a sci-fi novel, but it's actually running on real hardware right now. We're looking at Dr. Melvin Sewell's brilliant prototype from his paper on algorithmic encoding and quantum hardware integration for scalar field dynamics. What's so wild about this is that it literally translates theoretical scalar field dynamics directly into executable quantum code. We're not just looking at abstract math on a whiteboard here. This is a deployable digital architecture running on today's actual quantum processing units.
So let's start with the big question driving all of this. How exactly do you simulate a scalar universe on a quantum computer? It's a massive hurdle, right? Because by definition, scalar fields are continuous and infinite. But modern quantum hardware, that operates on discrete physical realities, specific qubits and quantum logic gates. So to pull this off, you have to build a translation layer. You need something that can take the sweeping, infinite dynamics of an entire universe and compress them perfectly into the finite matrix-based language a quantum computer can actually execute.
To see how that works, this explainer is going to follow a clear roadmap. We'll start with the scalar quantum prototype, move into the mathematical foundations and mapping, look at building the software architecture, and wrap up with the true flow universe context.
All right, let's jump right into section 1, the scalar quantum prototype.
The absolute key here is understanding HXI, or the parameterized scalar Hamiltonian. Think of a Hamiltonian in quantum mechanics as the operator corresponding to the total energy of a system. In this prototype, it acts like a universal translator. It's the mathematical bridge that takes those continuous field variables and snaps them directly onto a discrete quantum grid, specifically a Hilbert space defined by a set number of qubits. Without this operator doing the heavy lifting, the quantum computer would literally have zero way to process these scalar dynamics.
Now, to keep things computationally viable, this entire setup is built on a foundational 2-qubit system, so n equals 2. Because qubits exist in superpositions, adding more of them expands your computational space exponentially. But with just 2, our state vector perfectly spans a 4-dimensional complex Hilbert space. Basically, it gives us a manageable, highly controlled mathematical sandbox to watch these particles interact without totally overwhelming the system's architecture.
Which brings us to section 2, mathematical foundations and mapping.
Let's peek inside that translation engine. You've got a few specific components at play here. First is key, your primary scalar parameter. Dr. Sewell uses 1.618 here as an example, which is a nice little nod to the golden ratio. Then you have G, the intersystem coupling coefficient. That dictates how strongly different parts of the system interact. What's really elegant is how these parameters map straight onto polyspin matrices. The Z-matrix tensor product handles the localized field dynamics, while the X matrices manage the cross-system interactions. It's this beautiful, seamless synthesis of abstract variables and concrete quantum operators.
And to actually put this into motion, we use the unitary time evolution equation. By taking the exponential of our Hamiltonian, multiplied by a time interval, delta t, we create an operator that calculates the exact quantum state at the very next moment in time. Think of this equation as the play button for a scalar universe. It defines exactly how these theoretical particles evolve as the clock ticks forward.
Okay, moving on to section 3, building the software architecture.
The actual codebase for this prototype is super clean and broken down into 3 modular steps. First, Hamiltonian.py constructs those mathematical matrices we just talked about. Second, Engine.py compiles and dispatches the state evolution. And third, App.py wraps the whole thing in a Streamlit web GUI dashboard. It's logical, it's elegant, and it genuinely makes some highly complex quantum mechanics surprisingly accessible. Looking a bit closer at Hamiltonian.py, this is where the math literally comes to life. Using the NumPy library in Python, the code hard codes the polyspin matrices, identity, X, and Z. Then a function takes your scalar inputs and dynamically generates a precise 4x4 matrix representation of the Hamiltonian. You are literally watching pure theoretical physics get instantiated as complex arrays right in the computer's memory. Once the math is set, Engine.py takes over and offers 2 distinct execution paths. This is really where theory meets reality. You can run a local simulator for perfect, idealized state vector evolution right on your own machine. Or you can target a real IBM Quantum QPU that takes your code out of the perfect simulator and pushes it into the noisy, physical reality of actual IBM hardware, like the IBM Brisbane processor.
To hit that real hardware, the engine uses Qiskit to bundle our math into a quantum circuit. It securely authenticates with an API token, fires that circuit across the IBM Quantum cloud, and beams the physical results right back to your screen. And Dr. Sewell packages all this power into a Streamlit GUI. It's an interactive control panel where you can dynamically tweak 5 core variables. You adjust the Z parameter, set the coupling coefficient, pick your time delta, choose your hardware backend, and just hit execute. It takes what could be an incredibly intimidating theoretical framework and turns it into a totally playable sandbox. When the simulation finishes executing, the dashboard automatically generates a visualization of your results, specifically a bar chart mapping the probability distributions of the final measured basis states. In a 2-qubit system, you're seeing the exact likelihood of measuring states like 00, 01, 10, or 11. It's a direct reflection of how your inputs force the quantum wave function to collapse. You're observing the localized physics of a simulated universe right in front of you. Finally, let's look at Section 4, the true flow universe context. This is where things get really fascinating. This highly technical prototype is actually framed as a digital artifact within a broader sci-fi reality. The documentation explicitly states it's certified by the Cosmic University of Echo Rift Studies IX, with Dr. Sewell credited as the academic dean and diagnostic architect. It totally blurs the line between hard software engineering and immersive world building. There's also a strict sovereign intellectual property notice embedded right in the source material. It legally anchors these fictional, multiversal mechanics in the real world. By using a Creative Commons license and securing a digital object identifier via a Zenodo repository, Dr. Sewell treats this true flow universe and its scalar dynamics not just as a story, but as registered, immutable intellectual property. But perhaps the most compelling takeaway is how this rigorous quantum math actually serves as the literal foundation for a narrative. The source material features a quote from Chapter 1 describing a character named Psycho Venga emerging from a rift between slip flow and counterflow, marked by an SH1 resonance. When you realize this entire storyline is backed by actual executable quantum Hamiltonian matrices, you have to ask yourself, how much of Psycho Venga's multiversal journey isn't just written on a page, but is already mathematically encoded in the qubits sitting on IBM's quantum cloud? Something to think about. Thanks for tuning into this explainer.